So for today's session, we're going to go over midterm 2 review, like any topics you guys are struggling with the most. So some topics were like UV, vis, and like the benzene reactions, like electrophilic aromatic substitution reactions. And then if there are no other topics, we could go through the practice exam that he posted last night, right? So for UV vis, here's the like general concepts you need to know for this class. That is going to be between like, let's say 100 and 400 nanometers, right? This x-axis here is going to be in the units of nanometers. The visible light is going to be between 400 and 700 nanometers. So let's make it mark there. This is UV, and this is visible light, right? Where this is going to be wavelength in the units of nanometers. Okay. So let's say we have electrons in this orbital here, and there's a higher energy orbital up there. So this arrow here is going to represent energy, right? The higher it is, the more energetic it is, meaning that it is going to be less stable, right? If we excite these electrons by adding some kind of energy like heat or light, like let's say we shine light through it, like that, it could get promoted. This is called a promotion to a higher energy state, right? Right now, it is in the lowest energy state, and that is called the ground state. The ground state meaning that it is the lowest energy possible, meaning that it is the most stable orbital, right? Once we excite that electron, this is called the excited state with higher energy, right? So this UV vis here has to do with electronic excitation. Right? In IR, that had to do with like molecular vibrations, like the bond vibrations to show what kind of functional groups we had, like a C triple bond C, double bond, or alcohol, carboxylic acid. That had to do with vibrating the bonds between the functional groups. For HNMR, that had to do with like electron spin splitting, where we put a magnet through it and then it spins the electrons, right? But for UV vis, this has to do with electron excitation, where we are exciting electrons to a higher energy orbital, right? So that is for UV vis. Okay. So once we put a molecule through a UV spectrometer, this is the graph we get where the y-axis is going to be absorbance, right? And then the x-axis is going to be wavelength in the units of nanometers. And it's going to have some kind of like broad peak like that, where the maximum of that graph is going to show your wavelength that the molecule absorbs. Wavelength. And this absorbance here, or the intensity, right? Intensity, think of that as absorbance. There is an equation for that, which is A equals epsilon times C times L. Where A is absorption. So let's say this is A. Absorption. Epsilon is molar absorptivity. Molar absorptivity. And this epsilon here is different for each molecule. It's a constant, and it's basically saying how much light it can absorb. Some molecules have high molar absorptivity, meaning that they can absorb a lot of light. Some molecules have low molar absorptivity, meaning that they can absorb less light. Okay. C is going to be your sample concentration. And then L is going to be your path length, the amount of length that it takes for the light to hit the molecule. So the intensity depends on all of these three factors here. Okay, so relating this back to Occam now, this relates to Occam by, like, let's say we have this molecule here versus this molecule here versus, let's say, this molecule here. Okay, so which one of these will have the, let's say, highest energy? Or another way to think about it is which one of these will have will be the most stable, will be the most stable system. Yeah, the most right one, because the most right one here has the most amount of resonance, right? Those double bonds there can move around more. So stability increases from left to right. What does that make the energy? Where would energy increase from? Left to right, right to left. That's right. Where the least stable molecule, it has the highest energy. The most stable molecule has the lowest energy. Okay. And this is going to go back to Gen Chem concept, where let's say we have wavelengths, right? Let's say if we have high energy, right, like a lot of energy, do we have a short wavelength or long wavelength? Right. So long wavelength would look something like this, right? Where the wavelengths between the two peaks are very long, right? That is low energy. So if you have a high wavelength, you have a low energy, right? But if your wavelength is very short, right? Low wavelength, high energy. Right? So they are inversely related as well. So that is going to be wavelength like this. Okay. Okay. Another way you could think about this is that stability and wavelength are directly proportional. So the more stable the molecule is, the higher wavelength it has, the longer wavelength it has, because the lower energy it will have. Right? The less stable the molecule is, the lower wavelength it will have, because it will have higher energy. Right? So those are like the relationships between stability, energy, and wavelengths. So I'm going to give you guys, let's say, 4 different molecules, and I'm going to give you guys, like, tell you guys to rank them in order of, let's say, increasing wavelength, where 1 is going to be the highest wavelength, and then 4 is going to be the lowest wavelength. Let's see. So rank these four molecules in order of increasing wavelength. One is going to have the highest wavelength, four is going to have the lowest wavelength in the UV vis. So for these ranking problems, I like to look at the extremes first. So I like to look at the number one and number four, and everything else is in between. So which one of these will have the highest wavelength? Yeah. Another way to think about it is which one of these is the most stable, has or the most resonance available, right? Because more resonance means more stability. So that one is going to be this far right one, because we see that the benzene ring here is doing resonance itself, but also we have this group right here on the benzene ring that has lone pairs of electrons, where these lone pair of electrons can donate electrons into the ring, increasing its resonance power, right? There's more resonance in this fourth molecule than this regular benzene with no groups, because the lone pair of electrons here gives it more resonance. And this structure here with that extra group is called an oxochrome. That might show up on the vocab, right? Which basically means you have a group on the benzene ring that can donate electrons, oxochrome. And oxochromes increase wavelength that the molecule absorbs of a molecule. Yeah, oxochromes increase because they give it more resonance, and by giving it more resonance, it is going to be more stable. And if it is more stable, it has a higher wavelength. So which one of these would be the fourth one, the one with the lowest wavelength, the one with the least amount, right? The one on the far left. This one here has the lowest wavelength because there's the least amount of resonance here. This double bond can't move here or all the way over here because this carbon here is sp3. That's an sp3 roadblock blocking resonance. Right. So now we're just going to compare this and this here. We know the benzene ring has like 3 resonance arrows, whereas this system here only has 2 resonance arrows. Since the benzene has more resonance, that is going to be the one that has a higher wavelength. And that was going to be number 3, like that. Any questions on this part? Oh, okay. Another thing is that when we talked about UV vis here, we are exciting electrons. We are promoting that to a higher energy state. And if you look at the difference between these two orbitals, think of that as the energy difference between them. We can calculate how much energy it takes to excite this electron to the next orbital by this equation here. let's see, E equals Planck's constant times speed of light over wavelength, right? These are constants. The Planck's constant and speed of light, constant. The wavelength is read from the UV vis spectrum, right? And then once you have that, you could calculate how much energy it takes to excite the electron. Energy it takes to excite electron to the higher excited state. Okay. A quick summary for this UV vis stuff is this right here. So let's say you have more resonance, conjugated system, or you think about resonance. Right? The more resonance that that system has, the higher wavelength it can absorb in the units of nanometers. And what does that mean about the energy? Is it going to increase or decrease? Yeah, it's going to decrease. They are inversely related. This also might help. That means that since it is like energy is decreasing, we are increasing stability. Yeah. Okay. We also went over oxychromes, and the wavelength that it absorbs, right? If it lands between 400 and 700 nanometers, it will reflect the complementary color of that. But I don't think that's going to be tested. Like, for example, let's say it absorbs green. Like I don't know what green is in here. But if it absorbs green light, it's going to reflect red light. But I don't think that's going to be tested. Okay. So let's do the UV Viz vocabulary questions on the practice exam. Let's look at G and H here, which is this G and H. For H, I'm going to write the equation. Oh, yeah, there you go. Okay. What did you guys get for part G? So in UV Viz, we are exciting electrons. So I think the answer here would be electronic excitations, where we shine light to give it energy and excite the electrons from the grounded state or the ground state to the excited state. So that's electronic excitation. The other ones here, nuclear spin flips. Like let's say we have electrons around like that, and we shine a magnet through it. It is going to, like, let's say, reorient itself like that. That's for HNMR. Right. Molecular vibrations, that's more for IR. Electronic excitations, UV vis. We are exciting electrons from the ground state to the excited state. Yeah, this is some other thing, molecular rotations. I think that's talking about like rotating signal bonds, but what did you guys get for H? What factors influence the intensity of a peak in the UV vis? Yeah, ethylene, or what was that? Sorry. Oh, path length. Oh yeah, right. Path length. That's right. Path length. This one of light and sample concentration. Right. Both of these factors here will influence the intensity of the peak. Right. These other two here, accelerating voltage and magnetic field strength, that's for mass spec, because that was part of the mass spec equation, the magnetic field strength and the accelerating voltage. That's more of the device, the mass spec device. But these two here, sample concentration and path length, affect the intensity of the peak. Okay. So that was UV vis. Do you guys want to go over like the whole practice exam now, or like just go over the new material? New material? Okay, new material. Okay. Let's see. We'll do the practice exam probably tomorrow then. So for new material, the benzene reaction, the common reaction that it does is electrophilic, aromatic substitution. You could abbreviate that as EAS. EAS. So here's the general pattern for these upcoming reactions. Let's say we have a benzene ring here, right? That is stable and aromatic. Stable, aromatic. If we introduce some kind of electrophile nearby, we know that the carbons of this benzene ring are nucleophilic because there are a lot of electrons from the double bonds here, right? So one of the carbons of the benzene, it doesn't matter which one, is going to attack the electrophile there, right? I'm choosing this carbon here to attack that electrophile. When that happens, we have this new bond between that carbon and that electrophile right there. This carbon here lost the bond, so that carbon would have to have a positive charge, right? So now this one here is, let's say, non-aromatic. It is unstable. We broke the aromaticity. So that's why we don't stop there. How can we reform the aromaticity? How can we return to our aromatic ring? Yeah. Hydride shift, right? Or elimination, E2 reaction or E1 reaction. We're going to, oh wait, so it's not a hydride shift where we're moving a hydrogen, but it's going to be E2 reaction, where we're going to make a double bond because we want a double bond right here. So we're going to deprotonate this hydrogen here. So E2 reaction. Right? Let's say some kind of base comes in. That base is going to grab that hydrogen and form a double bond there. There's no leaving group, so we don't kick out any leaving group. This was a carbocation, so this is an E1 reaction where we form a double bond there. And now our aromaticity is reformed. And we also get like this side product where the base is protonated. Okay. Okay, so let's go over ortho versus meta versus para. Let's say we have a benzene ring here with a random substituent there. Are you guys familiar with these position terms? Which ones are the ortho carbons, meta carbons, para carbons? Right. We know the ortho carbons are 1 away from that substituent. The meta positions are 2 away. Para position is parallel to the substituent, or 3 carbons away. Right. These carbons here are not always the ortho position because it depends on the R group, right? Because if your R group was down here, these would not be your ortho carbons anymore, right? Because these positions here are relative to the R group, right? If the R group is here, now your ortho groups would be these 2 carbons, not these 2 carbons. So in this one here, these are the ortho positions. These are the para positions. And this is the para position there. Okay. And we only use ortho meta para when there are only 2 substituents on the benzene ring. 2 substituents. If there's 3 or more or 1, then we can't use ortho meta para. Now, are you guys familiar with EDGs and EWGs, electron donating groups, electron withdrawing groups? Okay, yeah, that's good. So you notice how when I went over this EAS reaction here, our benzene ring was the nucleophile. So what group do you guys think is going to make this reaction faster? EDG or EWG? Right. If we want this to be more nucleophilic, have more negative charge, do we want to add an EDG or EWG here? Yeah, EDG, that's right. So EDGs are considered activators. EWGs are considered deactivators. So another thing is that EDGs are ortho-paradirectors, and I'm going to explain this through resonance. And EWGs are meta-directors, with one exception, which are the halogens, right? Where it could be Cl, Br, iodine. These halogens here are EWGs because they are really electronegative, but they are not meta-directors, they are ortho-paradirectors. And I'm going to explain that concept right now. Where let's say we have this benzene ring here with this EDG here, right? I'm going to draw out all the resonance structures. And let me know if where I push that lone pair down to make a double bond there. This double bond moves as a lone pair on that carbon. The lone pair of electrons here is going to make a double bond there, pushing this double bond to make a lone pair of electrons on that carbon right there. And that gives us this resonance structure. And there's one last resonance structure here, where we are going to move this lone pair of electrons to make a double bond there, and push that double bond to make a lone pair of electrons on that carbon right there. So these are all the resonance structures. Do you guys have any questions on how I got these resonance structures here? Like on like the arrows, on like why the bonds moved where they moved, or the lone pairs, why they moved where they moved? Right. Yeah. So we noticed that if we put an EDG on the benzene ring, we put negative charges on the ring. And where are the negative charges at relative to the EDG? Ortho and para, right? We see that this negative charge here is ortho to the EDG. This negative charge here is para to the EDG. This negative charge here is ortho to the EDG. So as a general thing, if you have any EDG on the benzene ring, you will have a partial negative charge on the ortho and para positions there, which is why your ortho and para carbons relative to the EDG are the stronger nucleophiles. They are stronger nucleophiles than the meta positions, because these meta positions here, we saw that there are no negative charges on those carbons, right? So that's why if we introduce some kind of electrophile, either the ortho position or para position would attack that electrophile. And there is a major product in this case. Do you guys know which one is the major product here? Yeah, it's a para. And that's because of less steric hindrance. Those two groups here are far away from each other, avoiding steric hindrance. In the ortho position, these two groups here are close to each other, having more steric hindrance. Right? So that's why the ortho is considered minor and the para is considered major. Yeah. Uh-huh. Oh, right, both, right, both. Yeah, because they're both it's very close. It's like this is like 40 something and this is like 50 something. Yeah, 50 something. Right. Unless you have something like this, like let's say you had EDG down here, and then you had something like this. And then you had some kind of electrophile, right? There's only one spot where it could go, which is the ortho position, because the para carbon here relative to the EDG is already blocked off by another group. We can't add another group at that para position. It can only go either here or here. Right? This could get more tricky, but because let's say we have something like this right here. Now we can't add it here, right? Even though this is still ortho to the EDG, if you see three groups in a row like that, that is very sterically hindered. It does not want to go there, right? This already has so much steric hindrance, it doesn't want to go there. But this ortho position here is less sterically hindered than this one because there's nothing here. The electrophile would attach onto there instead. Right? So steric hindrance is also a factor on this here. Electrophile there. This right here, steric. This para position is blocked. And this ortho position is open. Now let's look at EWGs. Let's say we have this benzene ring here, and we have this electron withdrawing group on that benzene ring there. I'm going to draw out its resonance structures again. This is an electron withdrawing group because this carbon here is positively charged, partial positively charged. It wants to gain electrons or withdraw electrons. And it's withdrawing electrons from that benzene ring through this resonance arrow there, which will pop the double bond onto that oxygen and give us these resonance structures here. Right? This carbon here lost the bond, so that carbon will have a positive charge. We could do more resonance. This one over there. And then the last resonance structure is there. So these are all the resonance structures with that EWG. Where we notice in this case, it's like the EDG where they introduce charges in the benzene ring, but this time it is not negative charge. It introduces positive charges on the benzene ring. And the positive charges we see here, they are ortho and para to the EWG, right? So let's say we had an EWG here. There will be partial positive charges at the ortho and para positions relative to the EWG, like that, right? That makes the meta positions here the best nucleophiles in this benzene ring, right? Even though there's no negative charge, the neutral atom is a better nucleophile than the positive charge atom, which is why EWGs are meta directors. Right? If we introduce an electrophile into this benzene ring with the EWG, the electrophile will attach to the meta position. Because we said that these meta positions are the best nucleophiles compared to these positive charge carbons. Yeah. Yes, you need a catalyst, solvent, but these are just like the general mechanism before we go over the specific reactions with the solvents and catalysts. Uh-huh. Yeah. Okay. Here's an exception. Halogens. Because let's say we have a benzene ring with bromine here. We know bromine has 3 lone pairs of electrons. So when we do resonance, right, we will have partial negative charges on the ortho and para positions. Because this bromine here has lone pairs of electrons, which can donate into the ring and give negative charges on the ortho and para positions to the bromine, right? But this bromine here is not considered an EDG, right? This is still an EWG by induction, right? Because halogens they have high electronegativity. So consider them as weak EWGs. They are weak EWGs. So even though they are EWGs, they are not meta directors because they put negative charges on the ortho and para positions. This halogen here, even though it's a EWG, it is ortho para director. So that's the exception. Okay. Now there are, let's see, 1, 2, 3, 4, 4 or 5 EAS reactions that would add different kind of electrophiles. Let's look at the first one here. Right. Okay. So the first one is going to be bromination or chlorination. So the general reaction is that if we have a benzene ring and react that with Br2 or Cl2, let's choose Br2 in this example. This has to react with a metal catalyst. So it has to be either iron FeBr3, or aluminum, AlBr3. That will attach a bromine onto the benzene ring. Since there are no EDGs and EWGs here, it doesn't matter which carbon we attach the bromine to. This is just an empty benzene ring, so it doesn't matter if I attach it here, there, or there. But if there was an EDG or EWG here, then it will matter where we attach the bromine. But for now, this is just a general equation where general reaction where if we put Br2 in some kind of metal catalyst, that would just substitute one of the hydrogens of the benzene ring into a bromine like that. So here's the mechanism. I'm going to draw out the Br2 like this. One of the BRs of the Br2 is going to attack the metal, iron or aluminum. That is going to give me this structure here. Where, what would be the charge of this bromine here with 2 bonds now? Yeah, positive charge. And this iron here is going to have a negative charge because it has 4 bonds now. So positive charge on that bromine, negative charge on that iron, right? Okay, so think of this right here that we just formed is a very, very good leaving group. Good leaving group. That leaving group, you could just say it leaves by itself. When it leaves by itself, it will form bromine plus electrophile, like that, right? Where this bromine plus electrophile is that bromine right there that lost the bond. Okay, now this is the electrophile we were talking about in the general reaction. We could bring in our benzene ring. Let's say that this carbon here attacks that bromine. That would give us this intermediate here. Right, where I chose this carbon to attack the Br+, which is why there's a new bond between that carbon and bromine there. This carbon here lost the bond, which is why it has a positive charge. Right. The last step is to reform the aromaticity because we broke the stable aromatic ring. Now we want to reform it by doing an elimination reaction. Right. So that's the hydrogen right there. And the base that does that is going to be this leaving group that left here. Right. Iron still has a negative charge because iron still has 4 bonds. Since it has a negative charge, think of the Br as the base. The Br is going to attack that hydrogen, form a double bond there, and give us that benzene ring with the bromine. And our side products would be HBr, the HBr coming from this attack right here, when the Br attacked the H, and also our metal catalyst. This is a catalyst because it gets reformed. We get our FeBr3 back. But the important thing here is this organic product here. Okay. Chlorination is the exact same mechanism as this, where like this is Cl, Cl. Everything's the exact same. It's just like replaced with Cl. Okay, now let's do nitration. So for all of these reactions here, we want to form an electrophile for the benzene to attack. For bromination, chlorination, the electrophile was that X plus right there. Right. So for nitration, here's the general reaction. Let's say we have the benzene ring there, and the reagents are going to be HNO3, H2SO4. That is going to attach a nitro group or NO2 to the benzene ring like that. I'm going to draw out the HNO3 into this form right here for the mechanism. Okay. Nitrogen, double bond oxygen, H. Okay. How can we convert this alcohol, which is a bad leaving group, into a good leaving group? Yeah. Uh-huh. Yep, protonated, right? And we can because we have a strong acid in the conditions. This H2SO4 here is going to be common for these reactions. That is going to be our acid catalyst. That is going to protonate that alcohol to become this good leaving group here, oxonium ion, where that good leaving group is just, like, let me label that as good leaving group. Okay, now think of this as an SN1 reaction. That's just going to leave by itself. The good leaving group just like leaves, right? And that's going to give us this electrophile here, where the nitrogen now has a positive charge because it lost the bond, right? Okay. So since that's electrophile, we could bring in our benzene now. And we do the exact same EAS mechanism that we did previously. One of the carbons attacks that nitrogen. When that happens, though, we have to move one of the double bonds onto the oxygen like that to conserve the octet row. That gives us this structure with a positive charge there. And then the very last step is to always reform the aromaticity, because we always break aromatic benzenes for these reactions, but the very last step reforms it. And our conjugate base here is going to be the HSO4 minus. Grab that hydrogen, form a double bond there, and give us our NO2 group, right? This whole thing right here is NO2. There's no charge here included because the positive and negative charge cancels out. Do you guys know if this is an EDG or EWG, NO2? EWG, right? Because the very first atom attached to the system is positively charged, EWG. This is different than NH2. If you see NH2, that's an EDG, because NH2 will have a lone pair of electrons that is partial negative. So keep that in mind, the difference between NO2 and NH2. So that is sulfonation. I mean, nitration. Now we're going to go over to sulfonation. Sulfonation. Well, the general reaction for sulfonation is that we have a benzene ring. The reagents are SO3, H2SO4, and we are going to attach an SO3H group there. Okay. Here's the mechanism. Let's draw out. Okay, so here's the mechanism. Um, we are going to protonate one of the oxygens with the strong acid. Here, H2SO4. That's going to give us this protonated group here. But this oxygen here is not going to be our electrophile. Our electrophile here is going to be on the sulfur. Right? And the reason why is because, let me just draw out the resonance structure to explain why that this sulfur here is the electrophile. Because if I draw its resonance structure like that, okay. Which one of these resonance structures is major and which one is minor? Think about electronegativity here. Which atom is more electronegative, oxygen or sulfur? Yeah, oxygen is more electronegative. So, let's see. But actually, ignore that. Ignore that resonance structure. Ignore that resonance structure. Don't think about that. Sulfur is weird. Okay. So the electrophile here is going to be this sulfur atom there. That's the electrophile. Let's bring in our benzene ring. One of the carbons of the benzene ring is going to attack that sulfur atom and pop the double bond onto the oxygen right there. Right. We don't want to attack the oxygen because if we did that, we would pop the double bond onto the sulfur, but that oxygen will have 3 bonds, which is unstable. Right. But sulfur, it can handle a lot of bonds. Like this has like 1, 2, 3, 4, 5, 6 bonds. So that's why that's going to be the better electrophile. Right. When we do that, we are going to get this SO3H group right there, where the final step is to reform the aromatic ring using the conjugate base HSO4 minus. That, which will give us this reformed aromatic ring here. This is the SO3H group right here. Right? And because oxygen is more electronegative than sulfur, that makes sulfur the partial positive charge and the EWG. So this SO3H here is an EWG, or a meta director. Right? Now let's do the last two EAS reactions, the Friedel-Crafts reactions. Friedel-Crafts alkylation and Friedel-Crafts acylation. Friedel-Crafts alkylation. So let's say we have a benzene ring like this, and we put that through these reagents here. That R group with a good leaving group, chlorine, and a metal catalyst like AlCl3. We are going to get this product right here, where this is our nucleophile, and this here is going to be our electrophile. Because imagine this as an SN1 reaction. When the leaving group leaves first by itself, we are going to have this carbocation right here, right? Where that dot carbon right here is our electrophile, which is this dot carbon right here. This is our star carbon, the nucleophile. This is the new bond between the star and dot carbon right there. Right? And somewhere in the mechanism of this Friedel-Crafts alkylation is going to form a carbocation here. And whenever we form carbocation intermediates, do you guys know what we always have to look out for back in like the midterm one or midterm one material? Yeah, rearrangement step. So that's why Friedel-Crafts alkylation is not that good, not that used in lab. The thing that's more used is Friedel-Crafts acylation. Because let's say we try to make this group right here, this R group here, right? We cannot use that group with AlCl3 because think about the intermediate. When the leaving group leaves, right, we are going to form this carbocation right here. But we see that that carbocation can do a hydride shift like that and form a more stable carbocation intermediate at that tertiary position there, right? So that right there is actually our dot carbon, where when we react it, it is actually going to give us this product here, right? Not this product because of rearrangement. So here's going to be the mechanism for Friedel-Crafts alkylation. Let's say we had that same R group that we tried to use before with AlCl3. That R group with the halogen is going to attack the metal catalyst, right? Think about it like the chlorination reaction where the halogen attacks the metal and give us this intermediate here, where we know there's a positive charge on that chlorine because that chlorine has 2 bonds. And there's going to be a negative charge on that aluminum right there because that aluminum has 4 bonds. Think of this here as a good leaving group. But in this case, since this is a primary substrate, it cannot leave by itself first. This is going to go back to like 118A. Instead of like leaving by itself first, this is going to do something called a concerted hydride shift. Where we know that if it leaves, it's going to form this primary carbocation, but that cannot exist. So what happens instead is that this hydrogen right here nearby is going to shift over there and kick out the leaving group at the same time. And that gives us that carbocation right here, right? Which is this carbon right there, because that carbon used to have 4 bonds, 1, 2, 3, 4, but it lost the bond from this concerted hydride shift. The hydrogen in there just moved to that carbon, which let's say is this carbon right here, but it is now invisible. But I could draw that hydrogen out as that right there, which this hydrogen here is that hydrogen right there. And then it kicked out that good leaving group there. And that gives us this side product with the aluminum with the negative charge still because it has 4 bonds, and our electrophile here, where we could now bring in our benzene ring, attack the electrophile, and do the same exact last steps as regular. Let's say this is the star atom here. This is the dot atom here. Star atom, make a new bond between the star and dot atom. This dot atom here is attached to 3 methyl groups. So we draw 1, 2, 3 methyl groups like that. Right. Tert butyl. this carbon here lost the bond, so that carbon will have a positive charge. Now the final step, reform the aromaticity using this side product here. This Cl is going to grab that hydrogen, make a double bond there, and give us this reformed aromatic ring, HCl, and the reformed metal catalyst here. So that was the mechanism for Friedel-Crafts alkylation, where there are 3 limitations for this reaction. We covered the first limitation already, or one of the limitations, which is rearrangement. So that, let's say it's limitation 1. Okay. The other limitation is over-alkylation. Limitation 2, over-alkylation. Okay. So let's say we have a benzene ring like this, and we put that through this R group with the leading group Cl, AlCl3. Right. If we add that R group here, right? What is this R group here? Is this an EDG or an EWG? It would be an EDG because this is an R group, right? And any R group is an EDG. So R group, EDG. Like it could be a methyl group, ethyl group, isopropyl group, any random hydrocarbon chain. And we said EDGs are ortho-para directors, right? This reaction would not stop here. This will actually, like, since it activated the ring, right? Because we put an EDG there, the benzene ring is now activated. This reaction will happen again. So we attach another R group para to that. It could also attach ortho, but I put para because that's the major one. And then once that happens, we could like keep overreacting, but probably it will just stop here because like it's gonna start getting sterically hindered, right? But that is the other limitation. It over-alkylates, it overreacts in synthesis, which is why we don't use this that often in synthesis. The other limitation, the last limitation here, limitation 3, is does not work on deactivated rings. Right? And what does it mean for a ring to be deactivated? Like what type of groups are on the benzene ring? Meta directors, right? EWGs. So let's say we had an NO2 group there, and we try to do Friedel-Crafts acylation. No reaction, right? Because this benzene ring here is too deactivated for this reaction to happen. Oh, here's an important note, right? Because okay, deactivated rings can still do bromination or fluorination, nitration, and sulfonation. Deactivated rings can still do all those reactions. They cannot do Friedel-Crafts reactions. And that is important for synthesis. Friedel-Crafts reactions. So like alkylation or acylation. Now let's move on to the last EAS reaction, Friedel-Crafts acylation. So let's say we have this benzene ring here, and we have this R group with that carbonyl, AlCl3. Right? We are going to attach this group onto the benzene ring here. A tip that I like to do to predict these problems is look at the Cl and then substitute that with the benzene ring, right? Because that whole other group with the carbonyl stays the same, but it just substituted the Cl with the benzene ring here. Right? Let's see. Pascal didn't really go over like the mechanisms in detail for these reactions, but let's just go over it just in case, because this reaction also requires an acid workup step. So here's the whole mechanism of this mechanism. Right. So let's say we have this acyl group and metal catalyst AlCl3. The same kind of first step happens. The chlorine attacks the metal catalyst and gives us this chlorine, AlCl3, negative charge or positive charge on the chlorine because it has two bonds, negative charge on the aluminum there. Right? Right. Where this is our now good leaving group, like we saw in the previous examples, good leaving group. Think of this as an SN1 reaction. That's just going to leave by itself. Right? And when it leaves by itself, it's going to form, oh, this is important here. This group here is called an acylium ion. Acylium ion. Right? Where this is actually the minor form of it. The major form of it is when the oxygen donates one of its lone pairs of electrons to make a triple bond between that carbon and oxygen, giving that oxygen a positive charge. Right? This is the major resonance structure, and this is the minor one, because all atoms here fulfill the octet rule. Right? This is the minor one because this carbon here is missing the octet rule. It's missing 2 electrons. But our electrophile here is actually going to be that carbon right there. Okay. So now let's bring in our benzene ring nucleophile and do the same EAS reaction. We choose one carbon to attack that electrophile, move one of the bonds of the triple bond onto the oxygen like that. Okay. When that happens, we are going to get this. No more double bond there because we used that to make a bond there. Positive charge here. Where this is the star atom here. This is the dot atom here. And that's the new bond between the star and dot. Before that dot atom was triple bonded to oxygen, but now it's double bonded because we moved that bond to oxygen right there. The other way that you could have drawn it is like draw the attack from this carbon to that positive charge carbon right there, which gives you this exact same thing here. Yeah. Oh, right. Yeah. So it doesn't want to attack the oxygen with the plus charge because the carbon here with the positive charge is going to be less stable. We said this was a minor one because that doesn't fulfill the octet rule, right? It wants to really gain 2 electrons. So So that makes that more reactive than this positive charge here. This positive charge is less stable than that positive charge. And if it's less stable, it's more reactive, right? Which is why that carbon is the electrophile instead of the oxygen. And then the same last step happens. We reform the aromaticity by doing elimination. Right? So we're going to bring in that side product that we made earlier with the negative charge in the aluminum. The Cl grabs the hydrogen, makes a double bond there. And that reforms our aromatic ring there with the acyl group. Right. It doesn't stop here because there's some other stuff that happens with it, but Pascal didn't go over this like next step, extra step. So I don't think he'll test you guys on it. Wait, let me make sure. He didn't go over this. Sulfonation, alkylation, acylation. Yeah. For the mechanisms that he did, he shortened like a lot of the steps. Like he skipped a lot of steps in the mechanism. But I'll just give you guys the full mechanism just in case. Once we have this point here, right? The oxygen with the lone pairs of electrons will attack the metal catalyst once again and give us this product here. Right. Where that oxygen is now attached to the aluminum, CO3, and that aluminum will have a negative charge, right? Now that's why we have to bring in the acid workup step, H3O plus. That would just get rid of that group and go back to what we had earlier. This here, it just like washes that thing off, washes the metal catalyst off. Yeah, that's the complete mechanism. Yeah. Yeah, why the carbon of the triple bond gets attacked instead of the oxygen? Yeah, so it looks like the oxygen here is also the electrophile, right? Because it has the full positive charge. But we also have a positive charge if we draw its resonance structure out on the carbon. The positive charge here is less stable than this positive charge on the oxygen because the oxygen already has 8 electrons, 2, 4, 6, 8. It has the full octet row, full octet. This carbon here does not fulfill the octet row because it only has 6 electrons, 2, 4, 6, right? And since it doesn't fulfill the octet row, it is less stable, more reactive, which is why this one is more reactive than that positive charge over there. So that's why we attack that carbon right there. This carbon is the exact same carbon as this right here, right? You didn't have to draw this form of it. You could have kept this form here and attacked that positive charge carbon there instead, right? That would give you the exact same thing over here, right? Because that carbon still got attacked, which is that carbon right there. So either one getting attacked still works, but it's always that same carbon right there that gets attacked. We don't attack the oxygen. Yeah. So let's do practice problems on these EAS reactions now. Yeah. Yeah, we maintained the carbonyl. Yeah, no problem. Because the acid workup here is just washing the metal catalyst off, right? It would like basically separate the ions. The carbonyl here does not change with the acid workup. Oh, how do you get rid of the carbonyl? Okay, that's a good question because that is good for synthesis to get rid of that carbonyl, right? Okay, so this is gonna go more into synthesis now, where we covered all of the EAS reactions: bromination, chlorination, nitration, sulfonation, phenolcalus, alkylation, acylation. Now we're gonna use all those reactions for synthesis, right? Let's say we have that carbonyl there, but we wanted to get rid of that carbonyl and get to this R group here. There are 2 reducing agents you could use the one he covered in class is H2 PDC, right? Which is just gonna cleave that carbonyl off, get rid of that carbonyl to get us that R group there, right? I don't know. I'll just give you guys the other one just in case you guys see it, but he didn't go over this in class. You could see zinc, mercury, HCl as well. It does the same thing. This reaction is called Clemmensen reduction. Just in case it shows up. Clemmensen reduction. But he didn't go over it. Both of these reducing agents will cleave the carbonyl and get to the R group there. Yeah. Oh yeah, that's a good question as well, because this benzene ring here is very stable with its aromaticity. It's conjugated. If there was just like an alkene there by itself that's not conjugated, like not aromatic, then that alkene would like go back to the alkane itself. Uh-huh. Um, for aromatics, right? Uh-huh. Because if you have a conjugated system like let's say this right here, that is conjugated, but it's not aromatic because it's not cyclic. Yeah, it's not cyclic. Right. Uh-huh. It will get rid of all. You can force it to get rid of the double bonds if you put a lot of heat on it, a lot of energy on it. But that's not like usually the case. Yeah. Oh yeah. So the mechanism you don't have to worry about for this. You just know that it reduces. Yeah, don't have to worry about that. There is a mechanism for Clemmensen reduction, but he didn't go over that in class, so I wouldn't worry about that as well. Just know that if you want to reduce that, use H2BDC and it just disappears. Yeah, gets rid of the carbonyl, and also this might help you remember. It adds two hydrogens on that carbon that, where the carbonyl was. Where those two hydrogens right there are the two hydrogens from the H2 BDC. Yeah, let's try. Uh, yeah, let's try these reactions here. Uh, the second one is probably the trickiest one. Yeah. The second and the last one, the B and E. But let's try those. Positive charge. Oh yeah. Oh, right. That's another way to do it as well. Because the way that I did it, right? I This is what I did. That's the same thing as this. It's just resonance. But when we do that, the sulfur has a positive charge right there. Mhm. Yeah, to react with that. Right. Mhm. Yeah. I don't know. Yeah. Oh, zoom out. Oh, zoom in. Yeah, yeah, yeah. Uh-huh. Let's focus on the first three. Yeah, first three. Yeah. Yeah. AlCl3 works the same way as FeBrCl3. Yeah. A tip or a trick, yeah, would be like the B part B. There's an intramolecular reaction that's gonna happen somewhere. Intramolecular reaction. Okay. Okay. Have you sent it? Fantastic. Oh, before you guys do the third one, um, you know how we said that if we have a benzene ring with the carbonyl on it, and to reduce that, we use H2, PDC, or zinc, mercury, HCl. That is going to completely cleave the carbonyl into the alkane like that. That like those reagents can also reduce an NO2 all the way down to NH2. So when you have NO2, you can reduce that to NH2. These are reducing agents here, H2PDC and zinc mercury HCl, which reduces a carbonyl down to the R group. It could also reduce an NO2 to NH2. Yeah, right. And another thing is that you could go backwards. You could oxidize them. You could oxidize that alkyl group and get back to your carbonyl using Jones, CrO3, H2SO4, H2O. That would oxidize this R group and add a carbonyl to the benzylic position there. To get back to the NO2 from the NH2, that is going to be a peroxy acid like RCO3H or MCPBA. That's going to oxidize the NH2 back to the NO2. So going forward, reduction. Going backwards, oxidation. But on your synthesis, you could have like had that group and then uh, this be the fourth arrow instead, or for predictive product. Okay, now let's do. So for the first reaction here, what kind of intermediate is going to get formed? What is that name of that intermediate? Yeah, carbocation intermediate, where we are going to have that carbocation there when the leaving group leaves. And then whenever we have that carbocation intermediate, we always have to look out for either a hydride shift or methyl shift. In this case, we could do a hydride shift there to give us that carbocation at the more substituted position there, right? So it's not going to be this carbon that gets attacked, but it's going to be this carbon here that gets attacked, right? So let's say I choose this carbon here to be my nucleophile. This is going to be my product here. Wait, let's say this is the star atom. This is the dot atom here. We see that this dot atom here is attached to a methyl group and an ethyl group. So we have to include that methyl group and ethyl group like that. So that's the product for that. But it could also overreact, like we said earlier, because we added an EDG, an activator on it. So it could keep reacting, keep over alkylating. Right. For this next one here, we see a carbonyl with a halogen. That is going to be Friedel-Crafts acylation, because our first step, we have AlBr3 or FeBr3. But now in this case, we can't choose like any of these carbons to attack that carbon right there, because we know this is our electrophile, that carbonyl carbon. We want to use the carbon that would make the most stable ring. So let's say this is carbon 1, 2, 3, 4, 5, 6, right? So our most likely nucleophile is going to be this carbon here that makes the 6-membered ring, right? So when I draw that out, I know I'm going to make a 6-membered ring like that, where let's star that atom, let's dot that atom right there, which that dot atom was the carbonyl carbon, right? The bromine there, it leaves in the mechanism somewhere, but the carbonyl stays there. Right? So this was an intramolecular Friedel-Crafts acylation reaction. Right? The example that I gave was intermolecular Friedel-Crafts acylation, where the acyl group was separate from the benzene ring. Like there was no connection between them. But in this case, the acyl group is in the same molecule as the benzene ring. And if the nucleophile is on the same molecule as the electrophile, that is an intramolecular reaction, which will always form a ring, which is this ring right here, where I did this 1, 2, 3, 4, 5, 6. Before, there was no bond between 1 and 6, but that is the new bond between 1 and 6 from the Friedel-Crafts reaction. Yeah, any questions on this? Yeah. Yeah, I know it makes a ring because you know how in a regular Friedel-Crafts acylation reaction, let's say a benzene ring like that, and I have some kind of acyl group like this, and I put AlCl3 on it. In this case, it doesn't matter which atom is our nucleophile. Let's say this atom here is the nucleophile, and this carbon here is the electrophile, right? I'm going to substitute this chlorine with that benzene ring right there in the reactant. That gives me this product here, right? Does this make sense so far, like how I got to this product from this Friedel-Crafts acylation reaction? It's going to be the same thing here, but this time our acyl group, like this could be Cl or Br, it's connected to the benzene ring. In this reaction here, they were separate. This is intermolecular Friedel-Crafts acylation. This is intramolecular. So we can't choose this carbon here to react, because if we chose that carbon to react, that's going to be, let's say 1, 2, 3, 4, 5, 6, 7, 8-membered ring. And then we're going to have to do something like this. Say 2, 3, 4, 5, 6, 7, 8. Yeah. And then that is a not good, not good ring. We want to use this carbon or this carbon here. It could have been, let's say, this carbon here. This is, let's say, one. Yeah. This is going to be like the exact same thing as this, but just rotated a little bit, right? Because both carbons here, this or this, makes the 6-membered ring. This makes 7-membered rings, that makes 8-membered ring. Yeah. So look for your most stable ring possible. This. So what do you guys think? Yeah. 2 equivalents are excess of AL BR3. So the first equivalence was to make this Br here with the positive charge and aluminum here a good leaving group that just gets kicked out first, right? And give that carbon there a positive charge. That's the first equivalence. The second equivalence was this part of the mechanism here, where at the very end, we just attack that with the carbonyl oxygen right there to get this structure and do acid workup to get rid of that. But in lecture, he didn't go over this step. So I wouldn't worry about the 2 equivalents. If you see just AlCO3, then that it would work. Yeah. But the second equivalence in that example is this part here of the mechanism, where the carbonyl oxygen attacks that second equivalence to form this kind of structure. But we want to get rid of that thing. And to get rid of that thing, we use acid to wash it off. Okay. Okay. For part C, what do you guys think is going to happen in the first step here? What's going to attach to the ring and in what positions? So a lot of these predicted product or synthesis problems is recognizing the reagent, which in this case, the first step is HNO3, H2SO4. And do you guys remember what kind of reaction that is when we have HNO3? Yeah, nitration, that's right. Where nitration adds a NO2 group to the ring. But in this case, we can't add it to any like random carbon here. Yeah, ortho and para, because this is an EDG, which is an ortho para director. So the NO2 group could either be ortho or para, right? And we said earlier that the para one is major because it has less steric hindrance. So that is the major product there. That's after the first step. The first step gets NO2, ortho, and para to the EDG, the ortho para director. What will the second step do here? The zinc mercury HCl. Think of that as H2PDC. Yeah. Yeah, it will convert these NO2 to NH2. That's right, NH2. Okay. So the first reaction is very similar to the first reaction of the last one, where instead of nitration, we have sulfonation. Oh. Okay, before we do this problem, let's go over this concept. Right. When we sulfonate, let's say, a benzene ring and put SO3H there, we could go backwards. Right? We could get rid of that SO3H group. And to go backwards, we need a strong acid like H2SO4 and heat, acid and heat. Right? This doesn't happen like by itself. Like usually there's a reason why we do this. It's to protect the para position, because you know how this is an EDG right here, which is an ortho para director. When we put sulfonation conditions on it, it will only attach to the para position, because think of SO3H as a big bulky group. So when we have an EDG there, that is going to block the para position like this. Right. We don't add it to the ortho position because this SO3H group is very big and bulky. Not good here. Too much steric hindrance. Right. The second step, yeah. Oh, S would be neutral in this molecule here. It looks like this here, SO3H. S and then OH. SO3H. SO3H. Neutral charge, no positive, no negative charge on the S here. Which is why this is a very bulky group, because we see like it has a lot of groups around it, which is why it doesn't prefer to be in the ortho positions here. It prefers to be in the para position. And this right here is called blocking the para position technique in synthesis, in this benzene synthesis position, right? Because sometimes when you want to get to this product here, like let's say we have the same R group, and we want a group ortho to that only. But this is an ortho para director. If we just go straight for nitration, we will get this and the para position, right? But let's say we don't want the para position at all. If we don't want the para product at all, we only want the ortho one, we have to block that para position using the sulfonation group. Once we block that position, then we could do nitration with that SO3H group still attached to the para carbon there, right? And then the very last step is just to get rid of that sulfonation group by acid and heat, right? So that's the reason why we added SO3H and then got rid of it at the end. SO3H was used as the blocking group. It blocked the para position. Right. Okay. Let's see. So for part E here, we know this is going to be a Friedel-Crafts acylation reaction because we have this acyl group with AlBO3. So after the first one, we get this kind of intermediate here, right? Where we substituted that Br with that whole benzene ring here to get this product here, right? What do you guys think is going to happen next? Does it stop here or will it react again? It will react again because we have another acyl group here. So we do another Friedel-Crafts acylation, but this time intramolecular. So let's say this is carbon 1, 2, 3, 4, and we're gonna make a 5-membered ring where this is the nucleophile, this is our electrophile, and that's gonna give us this 5-membered ring, the carbonyl there, carbonyl here. Where this is the star, this is the dot. 1, 2, 3, 4, 5. Right. What would the last step do here? Zinc, mercury, or think of it as H2PDC. Yeah. Get rid of the carbonyl. That's it. Nice. That's it. Yeah. The third part. Oh, this. Oh, the part of D. Oh, like from here to here. I see, I see. Mhm. Okay. So after this last predicted product one, let's do last synthesis. Okay. Okay. So this one here, we said it is like H2PDC. It will reduce both the carbonyl down into the alkane or the alkyl group, and then the NO2 to NH2, giving us this product here. It will reduce both groups like that. Yeah. Uh-huh. Yeah. All right. H plus H2O is an acid, which that acid will, because we have excess AlBr3, that would get this somewhere in the mechanism. AlBr3, negative charge, positive charge, negative charge, positive charge. And then it just cleaves that whole thing off to get to the carbonyl only. Yeah, the zinc mercury gets rid of the whole carbonyl itself, right? The H plus H2O just gets rid of that metal catalyst. It keeps the carbonyl there, right? Uh-huh. Yeah, the acid workup, the one that washes off the metal catalyst, right? Did I include positive charge in that carbonyl in the mechanism? Yes. Oh, right. When this happens, right, when the when the oxygen, carbonyl oxygen attacks the metal catalyst, this oxygen here with 3 bonds will have a positive charge as well because it has 3 bonds. 1, 2, 3. Okay. Now let's do synthesis. Uh-huh. Okay, let's try this synthesis here. Another important thing that you might have to know for this reaction is that the only time you use Friedel-Crafts alkylation over acylation, because we always say alkylation is bad, like we don't use that, but this is the only time when you use Friedel-Crafts alkylation. Alkylation, right? Is when you want to get this kind of group right here, that isopropyl group, which is going to be, say, that and AlCO3. We cannot do acylation here because if we try to do that like same like carbonyl group and we try to add a chlorine there, there's something wrong there, right? This carbon here breaks the octet rule. There's way too many bonds. That's like 5 bonds. We can't do acylation if we try to do the uh, if we try to add a secondary carbon here, isopropyl group. Right? So no acylation in this part. We can only do alkylation if we try to add an isopropyl group there. Yeah. Oh no, it doesn't matter. It could be bromine as well. Yeah, bromine or chlorine. Any good leaving group. That is a halogen. What is the relationship between these two groups? Are they ortho, meta, or para to each other? Ortho, right? So let's say that that group was already there from that reaction. This is an ortho para director. We see nothing in the para position. How can that happen? Like if we try to add that Friedel-Crafts acylation reaction there, right? Because we know the first step is going to be Friedel-Crafts alkylation by adding this kind of reagent, AlCl3, and have that right there. We can't go from here to here right away using acylation, AlCl3. A tip for like to predict what kind of reagent you need for acylation is draw out your whole acyl group here, and then that bond attached to the benzene ring was your bond to the Cl here, right? Because this bond to the Cl just got substituted with that whole benzene ring there, right? We cannot do this because we said this is an ortho-para director. If we do this right away, we would also have the product with the para position. What can we do to block off that para position? Yeah. Oh yeah, it does over alkylate, but that's more for predictive product. Like if it's predictive product or explanation question, then that it will over alkylate. But for synthesis, you could add it once. Right. Yeah, you can do one EQ. Right. Yeah. Yeah, sulfonation. Sulfonation is gonna block off that para position. So think of that as a helper reaction. We don't want that sulfonation group in the product at all, but we need it there in the synthesis to block it off, to block off the para position, because we don't want anything in the para position. And then from here, I was gonna say we are going to do acylation, but there is a typo in the key here as well. I just realized. But what's wrong here? Why can't I do acylation in this ring? What is the problem here? Think about the limitations of Friedel-Crafts reactions and what kind of rings do that not work on. Yeah. Oh, that's more for steric hindrance, right? For Friedel-Crafts reactions, they do not work on deactivated rings. And what does it mean for a ring to be deactivated? Yeah, metadirector or electron withdrawn group on it, right? We see there's a very strong electron withdrawn group here. This strong electron withdrawn group would not allow us to get to the Friedel-Crafts acylation. It's a limitation for alkylation and acylation. That's the only limitation for acylation, right? Acylation will not rearrange because we don't form a carbocation. It will not over alkylate because when we do acylation, this is an EWG. It's not activated. But the only limitation it has that it does not work on deactivated rings. This is a deactivated ring here. Right. The key said that it does acylation, but I think that's a typo because it doesn't work on deactivated rings. Uh-huh. When we do directing groups, the EDGs will overpower the EWGs. So that's the ones that's directing it. We have an EDG here and an EWG here, but this right here is a weak EDG. This is a strong EWG. So this will still not work here. So there's a problem with this synthesis problem. This is ignore that synthesis problem. Yeah. Uh-huh. The Friedel-Crafts reactions. Yeah. Okay. If the EDG is stronger, this is a weak EDG because there's no lone pairs of electrons there. Yeah. Yeah, that chart that I give you with the strength of the EDGs, EWGs, you can look at that. I wouldn't memorize that though. I would think about these three factors here, right? If there's, let's say, a negative, like a lone pair of electrons on it versus, let's say this is alcohol versus this random R group. We know this is a stronger EDG because it has lone pairs of electrons on it, right? Now let's compare that with this. Both of them have lone pairs of electrons, but one is a stronger EDG, right? This nitrogen here is a stronger EDG than the oxygen because nitrogen is less electronegative than oxygen, meaning that it is more willing to donate electrons than oxygen. Oxygen is more electronegative than nitrogen, so it wants to keep its electrons. It doesn't want to donate its electrons. Nitrogen is less electronegative. It doesn't want to keep it as much as oxygen. It's more willing to donate and give it up to the benzene or whatever system it's on. Right. So that's the factors that you can think about: lone pair of electrons and electronegativity. The other factor you could say is negative charge, because if we have like this versus this is a stronger EDG because it has a full negative charge. Yeah. So instead of memorizing that, think about these factors here to determine the strength of the EDG. Right. For EWG, your strongest EWG is going to be NO2, which is going to be something like this. Right? Because we see that this nitrogen here has a full positive charge. Right? And one of your strongest EDGs is going to be your NH2 because it has a lone pair of electrons. And it's on a nitrogen that is less electronegative than oxygen. So that's the polar opposite, NH2 and NO2. NH2 is a strong EDG, a very strong EDG. NO2 is a very strong EWG. Okay, let's try Pascal's synthesis problem on this like benzene stuff on the practice exam. Oh my gosh. Okay, here. Oh no, that's Leo's order. Synthesis. Right here. Okay, yeah. Yeah. Try that for 2-3 minutes. So tips for this synthesis problem is to look at the relationship between the two groups. Are they ortho, meta, or para to each other? And then see what kind of directing groups you want on the benzene ring first, ortho para director or meta director. And there are certain helper reactions that you could use, like the blocking the para position from sulfonation, or reducing a carbonyl down to the alkyl group, R group, right? Because that carbonyl there made that group an EWG, but when we reduce it, it becomes an EDG because it became an R group. Right? The same as NO2 to NH2. NO2 is an EWG. We could reduce that to an EDG by making it into NH2. So let's try this. Yeah, that's right. This is an ortho para director, and this is an ortho para director. So when we add one group first, we can't add the other group right away because they're not ortho para to each other, right? But look at this R group here. What could have that come from? Like this could have came from a meta director. How could we make this into a meta director? Yeah, ketones. So the first reaction here we're gonna do is acylation. And like you said, that would create that ketone right there with the exact same R group, like that, right? Where this Cl here gets substituted with that benzene ring. That was the Cl there. Now, this is not an ortho para director anymore. This is a meta director. Where from that meta director, what's the next step? Yeah, we could brominate it using Br2, Fe, Br3, which will add bromine meta to that group, EWG. Now, there's one last step here. Yeah, H2PDC to reduce that carbonyl into the alkyl group. Nice, nice. The order matters here because this wouldn't work. If you try to flip it, like do H2PDC first, and then bromination, what would you get instead? Para or ortho, but para major. But that's not what we want in the product. So the order in these reactions matter a lot. So these red arrows here are the correct sequence, correct order, and correct reactions to use. The purple sequence here uses the same kind of reactions, but different order. And if you mess up the order, you get the wrong product because of the ortho para directing group or the meta directing group. Right? Yeah. Oh, to this position here. Right. So you know how this is an EWG here because this atom here directly attached to the benzene ring is partial positive. We know that there's going to be partial positive charges ortho and para to it, right? Because when we draw the resonance structure of that, there's going to be full-on positive charges on the ortho and para positions relative to the EWG, right? Like if I draw like resonance arrows like that, there's going to be positive charges ortho and para to it. Does that make sense so far? Right. That makes the meta positions here, even though there's no charge, the best nucleophiles because neutral charges are better nucleophiles than positive charges, right? So that's why if we do kind of reaction like bromination, chlorination, nitration, the electrophile will attach to the best nucleophile, the meta position, which is why EWGs are meta directors. It directs the electrophile to the meta position. In this case, this is an EDG, which is an ortho para directive because it adds negative charges to the ortho and para positions. It directs the electrophile to the ortho and para positions, right? But we didn't want that, so that's why we wanted to do this reaction from the EWG first instead. Yeah. Let's see. Tomorrow we'll do more of these benzene synthesis problems and the practice exam as well. Yeah, but today we just went over like the reactions from scratch. Yeah, no problem.